So yeah, all of those, those error formulas, they're all sort of helpful information, but that's probably going to be too technical for me to ask you about on the final. I mean, do I think that you should know it personally? Yeah, I mean, that you should be at least familiar with what's happening there, and that you can use that to find, how far off some estimate is potentially. But as far as the exam itself goes, I mean, that'd be kind of, I guess, out of bounds in some ways. Other questions? Yeah.
Can we do an example of like finding the distance from a point to a plane or like a line to a plane?
Yeah, sure. So point to a plane or a line to a plane, sure. So I don't know, let's go to the review problems. Oh, that would have been in chapter 11, right? So review exercises, chapter 11. Let's see here. Yeah, can I, what in the world? What, why does it do this? 110% here. Okay, there we go. So let's see. Here's some distance ones right here. Okay, so like 51, for instance. Just find the distance. Let's do 51, yeah. Okay, so find the distance from, or between the point 102 and that plane right there. Okay, so in this plane, what is the normal vector? Can you extract a normal vector for that plane just directly from the equation? Right, we saw that that's the coefficients of x, y, and z respectively will give that just based on the construction of the formula for the equation of the plane. Okay, and let's call this point Q. Okay, so Q equals that. Okay. What is a point on this plane? Can you think of a point that's on this plane? So point on the plane. P equal to, can you think of a point that's on this plane? Zero, two, no, not 0, 2, 1. Yep. 0, negative 2. 0, negative 2, 0 would work. Yeah? You have to think of something that actually satisfies the equation of that plane, correct? Now remember, the way that we found distance from the point Q, or from a point Q to a plane, was by projection, right? We did it by projection. What we did is we took a point in the plane, we drew a vector from that point to the point off the plane, and we projected onto the normal vector. Remember? And that involved computing the dot product. In the end, when we kind of thought about it, used a little bit of trigonometry, we realized that in the end, the easiest, or the way to get that projection was to take the dot product of the normal vector with PQ as a vector, and then we divided by the length of the normal vector. Yes? So what's PQ? What is the vector PQ? So in going from P to Q, how much X change is there? How much x change is there in going from P to Q? 1. How much y change in there is in going from P to Q? Again, you could do this by just subtracting coordinates, go Q minus P. But well, how much y change is there? 2. How much z change is there? 2. Okay, so you go PQ dotted with N. And again, this formula didn't come out of thin air. We got it from thinking about projections. So P dotted with Q is going to be 1 times 2 plus 2 times -3 plus 2 times 6. So what do we get here? So 1 times 2 is 2. Plus 2 times -3 is -6. Okay, so and then 2 times 6 is 12. 12 minus 6 is 6 plus 2 is 8. That's what the dot product is, 8, right? So what's the distance going to be? Well, it's going to be the absolute value of PQ dotted with N divided by the length of the vector N. Yeah, that was the formula we came up with when we thought about projections. So this is going to be 8 divided by the length of N, which is the square root of, what is this, 4 plus 9 plus 36 or something like that, right? Oh man, that worked out nicely. So what do we get? 8/7, right? I mean, if it works out that nice, you're pretty confident, yeah? What about like 53? 53 is, hopefully that makes sense. 52 is the same problem, basically, right? Find the distance between that point and that plane. We can do the same sort of thing, yeah? But any questions on that? What about this one? Find the distance between those planes. Now that's kind of a weird question. If I have 2 planes floating around in space, there's really only 2 options. Either the planes intersect each other, okay? Either the planes intersect each other, all right, you got to admit that's a pretty good picture, right? Either the planes intersect each other like that, or they're parallel. Yeah? Now, if the planes intersect each other, that means the distance is 0, right? If the planes are parallel, what would be an effective strategy for finding the distance between those planes? Yeah, that's right. You could just find a point Q on this plane and then compute the distance down to this other plane, right? So that distance right there, and then it would just become like the previous problem, yeah? How could I tell whether I'm in the intersecting plane or the parallel plane situation? Yeah, that's right. So their normal vector, in each case, the normal vector is 5, -3, 1. Do you know what I'm saying? Okay. So they have parallel normal vectors. So therefore the planes themselves are parallel. Yeah? So then all you have to do is pick a point Q on this plane. Can you think of, okay, so what? So Q equal to, or actually, no, let's use, well, you know, whatever. Let's pick a point P. No, yeah, Q, all right? What is a point Q that happens to be on that first plane? Yeah, 0, 0, 2 is a good one, for sure. Okay. 0, 0, 2 is on that. Okay, is on the first plane. Okay, what about on the second plane? 0, 0, -3 is on the second plane. Okay, what's PQ? What's PQ? 0, 0, 5. Okay, and now you're just going to proceed like you did before. The distance between those planes is the distance from Q to the second plane, for instance. Yeah, and now we're good to go. Proceed exactly like we did in the previous problem. Okay. There might be, I feel like there might have been a different one. Find the distance between the point, that point and that line. You remember how we did that? How do I find the distance between that point and that line? What did we do? What's that? I mean, you could. Yeah, you use the cross product. You do the length. You do like a PQ thing. You take a point on the line and then the point off the line. You do the PQ thing. And you don't use a normal vector. What do you use? You don't use, I mean, because you don't use a perpendicular vector. What do you use instead? So, I mean, here, let me draw you a picture, okay? Let me go somewhere where I can actually draw something, like right here in between these two parts right here. So watch, here's the line, okay? Here is a direction vector on that line. I don't know. Okay, let's call this vector, here's the direction vector. Let's call this V, all right? Okay, that's the direction vector for the line. Here's a point Q right here off the line. Let's call this point P that we're drawing V from, emanating from. And then what we do is we form this vector PQ. You kind of think of this angle right here between these two. And then what we do is we complete this triangle right here. Oh man, I just erased a bunch of junk. What in the world did I just do? That's all right, hang on. Oh wow, I used the wrong color. So there's V right there. And then what we're going to do is we're going to complete this triangle, okay? Okay, so I want this distance D right here, correct? What trig function am I going to use? Sine, because it's opposite, yeah? So D is going to be equal to the length of PQ sine of theta, yeah? And then you say to yourself, well, for crying out loud, that's annoying. I would have to know what that angle is. So what you do is you multiply and divide by the length of the direction vector, because the direction vector is the vector I computed the angle. I computed the angle between the direction vector and PQ, correct? So I multiply and divide by the length of the direction vector. Why do I do that? Well, because this junk right here, length of PQ, length of V times sine of theta, guess what that is? That's the length of the cross product. Okay, so we get the formula D is equal to the length of PQ crossed with V, the direction vector, over the length of V. Yeah, so it's a formula that almost looks like the previous one. Yeah. So that was the picture we came up with last time. Okay. or several times ago, I guess, at this point. Well, that said, you go up here. What's the direction vector? Okay. Okay, so what is the direction vector for this line that they've given us here? V equals 1. It's the coefficients of t, the parameter, remember? So it's 1, -2, -1, right? And then what's a point on the line? Can you give me a point on the line? 135 is obvious because you can just take t equal to 0, yeah? So 135. Okay, what is the point that we want to compute the distance to? -513. And then finally, so we need to do PQ. Okay, well, PQ, okay, if I go from P to Q, how much change has there been in the X coordinate? -6. How much change has there been in the Y coordinate? Isn't it -2? Yeah? And what about in the Z coordinate? -2. So then in the end, you have to compute the cross product of those two things, compute the length, and then divide by the length of V. Yeah? And that will give you the distance. But those are all, that's all the component parts that we need to pull this off now. I have PQ, I have V, compute the cross product. So D is equal to the length of PQ crossed with V divided by the length of V. That was the formula we came up with, okay? What else? Other questions? Other questions? Yep, Kara. Sorry, can you say again? No. I mean, torque, that was a particular application of the cross product, if you'll recall, but it's pretty specific. So, projections? Okay. Okay, so so like 29, for instance. Okay, it says find the projection of U onto V. Now, if you forgot the formula for projection, you can kind of come up with it again. Okay, so like if this was U and V was like this, okay, then the projection of U onto V, right, you kind of go like this. Okay, so this would be proj, and it's kind of weird the notation they use, but you even though it's like in the same direction as V, you think of U going on to V like that, yes? So how do I figure that out? Well, first of all, what is the length of the projection? Right? I mean, I'm just trying to re-remind you of some things just so you can kind of think this through in case you forget the formula or something. Okay? Well, the length of the projection, okay, that's like that adjacent side of that right triangle. Don't you see? Yeah? It's the adjacent side of that triangle. Therefore, what trig function would we be using to find the length of the projection? I would use which trig function? Cosine. So the projection, that's equal to the length of u cosine of theta. And then you say to yourself, well, okay, maybe I can multiply and divide by the length of v, right? Why would I do that? Well, because I know stuff about dot products. Because length of v cosine of the angle between two vectors, that is the dot product, correct? Okay, so the length of the projection is equal to u dotted with v over the length of v. Okay? Now I'm being a little bit sloppy here because actually that angle could be bigger than 90 degrees, and that could have been negative. Technically, I would have to take the absolute value. But we want to leave open the possibility that the projection could be in the other direction, could be in the opposite direction of v also. So that's what the length of the projection is. How do I get a vector out of this? How do I get a vector of that length in the direction of v? Do you remember how we do that? How do I get a vector of this length in the same direction as v? What would I do with this number? This is just a number. The unit vector in the direction of v, yes. So the formula ends up being, I want the projection of u1 to v. I'm going to take this number. I mean, I don't know, this number might be like 5 or something. What I do is I say, I want a vector that long in the direction of v, yeah? And so what I do is I take v and I divide by the length of v. I take a unit vector in the direction of v. And that's where this formula comes from, u dotted with v over the length of v squared multiplied by v, yeah? And by the way, the length of v squared, I mean, what's another way to say that? What's another way to, the length of v squared, what is that really? U dotted with v over v dotted with v, all times, that constant times v itself. Okay, so going down here, if u is 1, -1, 1, okay, so if u is 1, -1, 1, what's u dotted with v? U dotted with v equals, think about it, so it's going to be 2, 0, 2, and you add all those things together, and what do you get? Isn't it like 4, right? And what's v dotted with v? What's v dotted with v? Yeah, 2 times 2 is 4, plus 0 times 0, plus 2 times 2 is another 4, so it's 8. Okay, therefore the projection of u onto v is equal to u dotted with v, which is 4 over 8 over v dotted with v. And then you multiply this by v, which is 202. So what am I going to get? That's 1/2 times 202. So what do I get? 1, 0, 1. Yeah? That's it. Is that all right, Kira? You have another, so other questions? Other questions? okay? Arc length and area of a polar equation. Well, that's going to be in another section. Let me see here. Okay. So okay. R equal to, let's do this third one right here. The area of that polar region right there, that blue area that's highlighted right there. So let's do this problem. Okay. Oops. This problem. Okay. So I don't know, let's call this area A. If you think about it, so this point right here, where all the magic starts happening, that's at 90 degrees. Think about it. Isn't that right? So 3 minus 2 times the sine of 90 degrees. Sine of 90 degrees is 1. 3 minus 2 is 1. Yeah? Right? So that point happens when theta is pi over 2. This point right here, that happens when theta is 0. Yeah? This point right here happens when theta is 180 degrees. And this point right here happens when theta is 3 pi over 2. Yeah? So this thing gets traced out kind of in this direction for increasing values of theta. So where do I get my region? What values of theta would I have to run through to get that region? Pi over 2 to 3 pi over 2, right? So A would be equal to, now the formula is there's a 1/2, yeah? And it's going to be the integral from pi over 2 to 3 pi over 2 r squared d theta. Remember, we even reasoned out why it worked the way that it did. It had to do with the area of a portion of a circle. That's where that came from, the r squared, remember? Okay, so you would go 3 minus 2 sine of theta, quantity squared, d theta. So now it's just a matter of doing the integration, okay, and you know, being careful the way that we proceed here. So it's going to be 1/2 the integral from pi over 2 to 3 pi over 2. Okay, let's see here. If I square this out, it's going to be 9 minus 6 sine of theta. That happens twice, doesn't it? It's going to be minus 12 sine of theta plus 4 sine squared of theta, d theta. Now, the thing is, I know how to do the integral of the 9 part and the 12 sine of theta part. What do I do with this? How am I going to deal with 4 sine squared of theta when I'm integrating? Half angle. Right, you would use the half angle formula. So now it's just a matter of actually just going through and doing it. Yeah, used half angle formula. And remember, there's this factor of 1/2 sitting out here. Okay, so there's that. So we had to kind of think about when it is that we actually intercept that region. Okay, we got the proper range there, and then we had to think about, you know, what it's going to take to actually integrate this thing. Let's find one that's having to do with, let's find one that's having to do with arc length. Okay, so remember the formula for arc length. I don't know if you remember this or not, but hang on, it says in these use a graphing utility to graph the polar equation over the given region and use integration capabilities of the graphing utility. That's not very encouraging. That probably means that you're going to end up with something that's, you know, not integratable. That's not that surprising though, because the arc length formula has a gnarly square root in it. The formula for arc length was like, oops, not A, what am I saying? Not A, it was arc length. What was the letter that we used for that? L or something? Huh? Oh, maybe, yeah, I don't know. I'll use L for right now. L equals the integral from alpha to beta, you know, and then it was like the square root of r squared plus dr d theta squared. So you take the derivative of r with respect to theta squared d theta, yeah? So like in this first problem right here, for instance, it would be the integral from 0 to pi over 2. Okay. The square root, oh, this is exciting. The square root of, okay, r squared, that's interesting. That's going to be 4 theta squared plus, what's dr d theta? Squared d theta. Ah, okay. So then what would you do? Integral from 0 to pi over 2. I could factor out 4, couldn't I? And in the end, that's going to pull out a factor of 2. And you would have the square, because square root of 4 is 2. Square root of theta squared plus 1 d theta. How do you do that? No, you don't have to use imaginary numbers. Thank goodness. Yeah, Kira. I'm trying to think if you could actually do it that way. Maybe not U sub, trig substitution. Okay. Okay, so it's actually not that bad. So for instance, look, if you had the integral of 1 plus u squared du, you understand that's like the same thing, right? Forget about the fact that there's a theta in here or whatever. But basically it's this problem, yeah? So what would you put u equal to? Tangent. U is tangent of t, what's du? Secant squared of t dt, yeah? Right? Okay, so what's 1 plus u squared then? Or hang on, what would the square root of 1 plus u squared equal in this case? Yeah, that 1 plus tangent squared secant squared, square root, that would just be secant of t. Okay, and du, of course, is secant squared. Oh my goodness, are you serious? It's going to be the integral of secant cubed of t dt. That's horrible. But we've actually done that before. The antiderivative of secant cubed is something that we have done before. We did that in the trig integral section, yes? We had the integral of secant, remember, which was logarithm absolute value of secant plus tangent. We had integral of secant squared, that was easy, that's just tangent. Integral of secant cubed is not pleasant, but we still were able to actually do it. We used integration by parts, yeah? So I think that's why they said to use what? Use the graphing utility, but you could do this by hand. Okay, you could do this one by hand actually. But I'm just telling you, most of the arc length problems, so I'm just gonna say this equals dot, dot, dot. We've done that problem before. It's actually in a video on the integration by parts day. And then I think we did it maybe again when we were doing trig integrals. We even did the integral of secant to the 5th power, believe it or not. Okay. But these arc length integrals always, or almost always, end up being fairly gnarly. You end up with something, because of that square root, you end up with something that's sometimes not even possible to do by hand. And you have to resort to using a graphing utility, okay? All right, other questions?
Are there any other big trig substitutions that we need to know other than power reduction?
You mean half angle?
Yeah.
Right, half angle and double angle are things that seem to come up fairly regularly. Double angle sometimes comes up when you're doing trig substitution. Okay, so like the half angle formulas were, you know, cosine squared of t is equal to 1/2 1 plus cosine of 2t. Sine squared of t equals 1/2 1 minus cosine of 2t. Yeah. The double angle for sine of 2t is equal to 2 sine t cosine t. Okay. What about cosine of 2t? Right, double angle for that. Well, there were several versions of this. The most common one is like cosine squared of t minus sine squared of t. But you could also replace cosine squared and sine squared with their Pythagorean equivalent. But the other things that we tended to use a lot were the fact that sine squared plus cosine squared is 1, and that tangent squared plus 1. And do you realize that really those are the same identity? I mean, let's just be honest here for a minute. If I multiply, right, I mean, I don't know if you realize that or not, but secant squared t, I'm telling you, you get to, right, you can get to the sine cosine identity by multiplying through by cosine squared. Do you realize that? Yeah? And you can get this guy by doing what? By dividing by cosine squared of t. Don't you see? Okay. Really, those are saying the same thing. There's actually, I mean, for as many sort of trig identities as there are and that, you know, we torture you with, there's really very few true trig identities floating around. All of those trig identities really are kind of just some trigonometric or algebraic manipulation of some kind. And all of it lives, remember that picture I drew at one point, like in the first quadrant, that all of it stems from that picture too. So, yeah.
You said we need to use GeoGebra for some part of this. What all do we need to understand how to do it?
Not much. It's pretty simple. I mean, like making a curve. So just go. Oh, what's going on here? Stop. Stop. Oh man, this thing is freezing up. Okay, well, I'm gonna open it up again. GeoGebra, there it is. Okay, so like if you make a curve, like you can go curve like this, and then you just select the appropriate thing, and it'll sketch space curves for you. Okay, so like if I do this, and I say, I don't know, suppose x is like, 2 minus t, and y is 3 plus t squared, and z is 5t minus 6 t squared or something, I don't know, okay? Parameter variable t, start value -10, end value 10, I don't know. And there's the curve, yeah? Okay, it automatically does it for you, and it kind of shows you what it's doing. So there's what that curve looks like. Oh, that's interesting. Okay. You can like zoom out, get more of an idea of what's happening here. Yeah, but yeah, GeoGebra is pretty nice. I mean, I'm literally an imbecile when it comes to like GeoGebra. I start typing stuff and it does it. There's like a little help menu in here too. Where's the help menu? I've used the help menu a lot. Maybe it's right here. Help. See how it says help right here? So there's like a lot of little tips and pointers. By the way, if you go here, like this little, here's the calculator. If you go in here, there's all these kind of built-in things that you can make in GeoGebra right here. Yeah, which is kind of nice. All right. Well, thank you. Again, if you have your whiteboard, you can turn that in. Not, I can turn in later. If you want to just keep it, it'll just be $5.
I had a quick question about
Uh-huh.
homeworks.
Oh, okay.
It seemed pretty simple, but for some reason it wasn't working.
Okay, hang on a sec.
Yeah.
Oh, yeah, I'm down.
Okay, which section?
It was 12 to
Okay.
19.
Oh, wait.
See ya.
C. So would you just multiply that vector value function of u by root t squared and then the derivative?
No, so I mean, if you have d dt of some function, some scalar function of t times a vector function of t, then it's going to be f. You kind of use the chain rule: f prime of t, u of t plus f of t, u prime of t. So in this particular case, what is it going to be? So in this case, f of t is 3t. So what's the derivative of that? Right, so it's going to be 3, and u of t here is apparently 4t, t squared, t cubed, right? And then it's going to be plus 3t times, okay, what is the derivative of u?
4 2t 3t squared, right?
Mm-hmm. So then what's this going to be? So if I, distribute, then it's going to be 12t plus 12t, right? So that's like 24t, right? And then what? 3t squared plus 6t squared. Do you see what I'm saying?
Mhm.
There's like 9t squared, and then what?
3t cubed plus
9t cubed, so it's 12t cubed.
Okay.
So, and I think you have to be careful about the way you input these things. You have to use actual vector stuff.
Yeah.
So,
I learned that the hard way.
so 24ti plus 9t squared j plus, plus 12t cubed. Okay, I just want to make sure this.
You could also do like the angled brackets, right? Like,
Yeah, probably so. I think, does that work?
I think so for the other ones.
Mine's weird. I only have one place that I can submit stuff. Yeah, that's right.
Okay. Thank you.
Yep.
Is there a way that I could get into the Calc 3 class that you teach next year?
I don't know. I mean, they've sort of said not to be signing people in yet. Just it's because it's hard to know who's going to actually be in that class and who's not at this juncture.
Okay.
I mean, you could always revisit it at the beginning of next term, but yeah.
Okay.
Yeah. Just stay on the wait list for now, but yeah.
Do you believe in spontaneous human combustion?
I don't know. There's it's weird. I don't know what